Hello, everyone. So in this meeting, we're going to talk about two chapters, Chapter 8 and Chapter 9. Chapter 8 is about sampling, population, and the sample. So how do you choose the sample from the population? And then Chapter 9 is about research design. So what kind of study do you design? How are you going to design your work if you want to, prove some point? So we're going to go over those symbols we use in the class real quick again. So we learned quite a lot of them already. So please spend some time on the symbols. Don't get confused. So small n is sample size, and big N is population size, and sigma, population standard deviation, and S, sample standard deviation, mu, population mean, so average of the entire population. X bar is sample mean, so average of the sample. Z is a distribution. It's a standard normal distribution. So this is a variable for a standard normal. R is correlation. We just learned about a correlation to show the linear relationship between the two variables. And B1 is the regression coefficients, and this is the slope. And B0 is the other coefficients, is regression intercept. P-value and alpha, they're both used in hypothesis test. P-value is a probability. So think about if you draw a sample from the population, when you randomly draw samples, then you could have many, many different possibilities, right? So then, but you only collected one sample from the population to do your research. So that p-value is how likely are you able to see the sample that you actually collected. So that's what the p-value is. So probability of observing a sample as extreme or more extreme than the sample being collected, right? So then we compare p-value with alpha to make a decision in hypothesis testing. This will be by very end of the course. So alpha is type 1 error, right? You don't need to know too much about it, just kind of getting some impressions. Then when the time comes, it will be a lot easier for you to understand. Right, so the learning objective, we have a few of them. We need to understand the relationship between sample and the population. We talk about sample and the population a few times already, so it's pretty straightforward. And then for the sampling process, we talk about the best way to do it is make sure your sampling process is a random process, right? You want to choose the sample individuals randomly. But sampling process could be very complicated. For different kind of research designs, you want to use a different sampling method. Even for random sampling method, there are still many different ways of doing random samples. So we are only going to introduce some simple process, and here we're going to use a table called a random digits table, and we're going to talk about how we're going to use that table to draw some random samples. There are a lot of other ways to do this as well. And understand the differences between observational study and experiment. For any kind of research study, you could be either observational study and experiment study. And we're going to talk about the differences between them. And then you need to get familiar with some terms in the study. So subject, factor, and treatment, they're very often used in experiment studies. Right, so we're going to start with chapter 8, producing data, sampling. So first, we need to understand the two groups, population and sample. And here we have a formal definition for those two terms. Population is the entire group of individuals that the researchers is interested about. So But the sample is only a small portion of the population of which the data are actually collected. So if you want to consider some individual as your sample, you have to know something about it. Basically, that's the idea. And then related to population and sample, we have another two term, very commonly used in statistics, parameter and a statistic. Parameter and statistic, they're both some kind of measures. Basically, they're numbers. Parameter is a number that describes the population, but statistics, a number that describes the sample, is calculated from the sample. So basically describing the sample, right? So there are quite a few measures we learned already, and all the measure based, most of the time, if you calculate something from the sample, that's a sample statistic, right? So let's list some of the measure we learned. So for example, we have two groups, population, and we have sample. These are the two groups, right? So then we have learned a few things in the calculation formula. For example, we know for sample, there's a sample size, right? And the sample size, we use the letter N represent. And for population size, we use a big N represent, right? And the small n is a measure describing the sample. So small n is a statistic, while big N is a parameter. So anything related to population is a parameter. Anything related to the sample is a statistic. That's pretty simple, right? And then we have a few other things we learned as well, right? So for example, we learned mean of the sample, right? So mean of the sample, we use symbol of X bar. I'm gonna find, oh, here. Want to make this a little too small. I couldn't find it very well. I think it's here. All right. So this is X bar. And then mean of the sample is X bar. The mean of the population is a different symbol, right? Anyone recall what it is? It's mu, right? So I can find mu here, okay? So mu is a population parameter, X bar is a sample statistic. And then likewise, we learned another thing to measure the sample as well, standard deviation, right? So the standard deviation for the sample, we use the symbol S represent, but while standard deviation of the population, we use a different symbol, and that's sigma, right? Okay, so sigma is a parameter, S is a statistic, and so on. So we also learned correlation, right? So we just calculated correlation from sample or population, sample. All the data you collect is the sample data. So then correlation you calculated, we use R represent, that's describing the sample, so it's a statistic. But there should be a correlation in the population as well, right? So that we use a different symbol. This is not required, but if you're interested, the population correlation will be rho. Okay, so the pronunciation here is rho. Okay. Then we also learn the regression process. So we have regression slope and we have regression intercept. So regression slope, we use B1, and regression intercept, we use B0, right? So these are statistics as well. They're describing something about a sample, right? And a population regression slope. If there is a linear relationship in the entire population, there should be a slope for that as well. So we use a different symbol, and that will be beta. Let's try to find a beta. Is it a special character? No, just symbols. This look like it, but not quite. Oh, here. So this is beta 1, and then the intercept, we call it the beta 0. Right? So then you have a list of population parameters on the left. You have a list of sample statistic on the right. Okay. So parameter and the statistic. They're both measures, but parameter measures about the population, and statistic measures about the sample. Right. So if we know what the population and samples are, then we should be able to identify population and sample when you read a research paper or a project. They're always going to describe it, but they're not going to tell you, hey, population is this, population is that. But when they state it, when they write it out, they're going to indicate what's their population, what's their sample. So, for example, let's read a couple of examples that identify the sample and the population. So a political scientist wants to know how college students feel about the social security system. So from this sentence, basically the research interest is already given, right? So the researchers interested in college students, and that's our population basically, right? Population is the group of individuals the researchers is interested in. So that's the population right there. And then if you keep reading, she obtains a list of the 3,456 undergraduates at her college and mails a questionnaire to 250 students chosen at random, and 104 questionnaires are returned. So then what's our sample? The sample will be the 104 students who returned the questionnaire, right? So that's our sample. The next one, a department store mails a satisfaction survey to people who make credit card purchases in the store. So again, from this sentence, it tells us the research interest already. The people who make credit card purchase at the store, that's what they're interested in. So that is the population of the study, right? And then this month, 45,000 people make credit card purchases and survey are mailed to 1,000 of these people chosen at random. And 137 people returned the survey form. So what's our sample? Our sample will be the 137 people who returned the survey form, right? So the sample is only the group individuals you actually obtain the data from. If they didn't return the survey, you didn't measure anything from them. So they're not your sample if that's the case, right? So it's pretty straightforward, right? Population and sample. All right, so I'm gonna continue. This is another practice, and this will be what you're gonna see by the end of the semester when we do inferences. So we're gonna provide a lot of information in a paragraph, and then you will need to be able to read the paragraph and then identify each of the measures provided, and also eventually you need to be able to solve the problem. Right, so the lifetime of a tire manufacturer manufactured by a company has a normal distribution with a standard deviation of 5,000 miles, and its average lifetime is claimed to be 45,000 miles. Last month, 7,000 tires are produced, and the inspection team randomly selected 30 tires to test for the lifetime. After the data are collected, it's found that the 30 tires lifetime has an average of 43,000 miles with a standard deviation of 6,500 miles. So then from the sample, what's the population and what's the sample, right? So basically population is the research interest. When they are testing the tires, what's their interest? Are they only interested in the 30 tires they're testing, or they're interested in all the tire being produced, right? So basically this is a quality control, right? When they control the quality, they're interested in the whole batch being produced, right? So in that case, the population will be the 7,000 tires being produced. All the tires, basically. And then sample will be just the tires being tested, right? So the tires you actually obtain the data from, that's your sample. And then when you keep that in mind, then we realize there are a lot of numbers given in the paragraph, right? We have 45,000, 7,000, 5,000, 30, 43,000, and 6,500, right? So what are each of those numbers? Are they a parameter or statistic? What kind of symbol do we use to represent it, right? So for example, if we go through the list, 45,000, is that a parameter or statistic? So how do I tell? Parameter is a number that describes the population, while statistics is a number to describe the sample, right? So in this case, is 45,000 describing sample or population? So when you look back, so it says the lifetime of tire manufactured by a company has a normal distribution with standard deviation 5,000 miles, and its average lifetime is claimed to be 45,000 miles. So when they claim 45,000 miles average, is it for all the tires being produced, or is it only for the 30 tires being, tested? And when you read between the line, obviously this is referring to all the tires being produced, right? So that should be a parameter because it's talking about the population. And then if you realize that's a population and that's population average, right? And population average is population mean, right? Population mean, we use a symbol of mu. So we got the first number figured out. Then the next number, 7,000. 7,000 is, we know that's referring to the entire population size, right? So it's describing the size of the population, then it's a parameter. And population size, we use symbol capital N, represent. And then 43,000, clearly it says 43,000 miles is average of the 30 tires, right? 30 tires is a sample. So it's describing the sample, so it's a statistic. And then average of the sample, it's sample mean. Sample mean, we use a symbol X bar represent. Okay, and next number, 6,500. 6,500 is right here. So 6,500 miles is a standard deviation of the 30 tires also, right? So that's a statistic because it's describing the sample. And then sample standard deviation, we use a symbol of S represent. And then 30, 30 is about 30 tires. Then 30 tires is sample, we know that. Then this is basically size of the sample. So we use small n represent. And then lastly, 5,000 is a standard deviation as well, right? But this standard deviation is referring to all the tires being produced. So that's a population parameter. And then population standard deviation, we use a symbol of sigma represent, right? So please, make sure you're able to identify all the symbols and able to match with, the numbers provided. So by the end of the semester, we're going to have some formulas involving some of the symbols, so that you don't get confused. You need to be able to calculate something correctly, by some given formulas, right? So now let's talk about sampling design. Sampling design is about how to choose a sample from the population to consider as a sample. And if you don't choose the sample very well, then you could introduce a bias. And a bias is something we don't want. Bias means the sample you collected doesn't really truly represent the population. The whole idea of drawing a sample is we're going to use a sample to predict something about the population. If the sample is biased, it doesn't truly represent the population, then we know whatever conclusion we draw from the sample will be wrong, right? So bias is just the design of the sampling process that could systematically favor certain outcomes of the study. Okay? So we don't want to introduce bias when you do sampling. So what kind of sampling design do we have? We're going to talk about a few. One is convenience sample. Convenience sample is easy to reach. So it's easy for the researcher. It's easy for the researcher to obtain a sample. So for example, if the university, some office, they want to know some students' opinions about some new policy changes, then the population will be basically all the students at MSU. Then, one way to draw the sample is, you need to get everyone's phone number or email and send them information, a survey, ask them to fill. But that could be pretty hard, right? Because getting everyone's email and phone number is not that easy, and they need to have someone to call them. And instead, you could just have someone standing outside of a building that students mostly visit, like a library or corporate center. So the person standing there just holding some surveys, or basically, or randomly choose some students passing by to ask them a simple question or ask them to fill a short survey. That way, it's a lot easier than calling everyone out or send emails to many people. In that way, it's convenience, right? So it's easy to reach. Next example is voluntary response sample. Okay, so from the name, basically, it's voluntary, and voluntary by who? By the participants. So it's up to the individual to decide if they want to be part of the study or not. And most of us has been part of the voluntary response sample. So think about, if you have done any survey online for invited survey, or at least, a lot of students have done the course evaluation, right? So the course evaluation is voluntary. You guys are not being forced to do it. So you guys up to your point to decide if you want to be part of the study. So that's another example of voluntary response sample. So convenience sample and the voluntary response sample, neither of them are really a random sample. There's no random process in either of them. So they could introduce bias. So for example, if we talk about the voluntary response sample for the course evaluation, so when do you feel like you want to be part of the sample for evaluating the instructor that you have for any semesters? Most of the time will be the instructor is very, very bad, or if the instructor is very, very good, right? So that could bring some bias in there. So only the students who have strong opinions will want to be part of the study. Also, just like the readings of some products, right? That's a voluntary response sample as well. If you buy something that's very, very good and you're so happy, you want to advertise for them, right? So you want to tell your family and friends, or tell people that, hey, this is worth buying. So you give them a good rating. Or if you buy something very, very bad, and you want people to be aware, so you also want to post something out so people can realize it. So voluntary response sample could introduce some personal bias in there, and that could favor one or the other outcome. And the convenience sample is the same deal. So for example, I give you another convenience sample example. So if a restaurant owner who wanna get some opinions about their food and service, so he decided to do a convenience sample. He gonna ask some familiar faces, the customer, to fill a survey for him. The reason he asked a familiar face because if you ask someone who don't come often, then he may not want to spend time to fill the survey for you, right? So in that case, it's easy for the owner to get the response, but what's the problem? Familiar face. That means the people who come to the restaurant often. And why would you want to go to a restaurant often? Most of the time it's because you like the food and service, right? So the results will be biased if that's the case. So that's, if you don't do a random sample, there's always a bigger chance of, introducing bias, and that's what we want to avoid. And the very, very common method in a lot of the study is called a simple random sample. This is one type of random sample process, right? So simple random sample will make sure individual from a population chosen in a way that every set of an individual has an equal chance to be the sample being selected, and also every individual has the same chance to be selected as well. And the good thing is you don't know anything about the individual that you choose as your sample. So you don't know it, so there's no bias in there, right? So then how do we do a simple random sample? What can we use to get a simple random sample from a population? There are many, many different methods, especially right now we have softwares. So you can use softwares to help you to get a random sample. But in the class, we're not going to use computers for the testing or anything. We're going to still use the old fashioned way. We're going to use a random digit table. But even if you use a software, still just basically there's a table in the software being embedded in there. It's the same process, right? Okay. So the random digit table look like this table. Basically, it's one full page of digits from 0 to 9 in a random sequence. So basically, from first number, you're going to randomly choose a number from 0 to 9, put it here, and then randomly choose another number, and again, choose a random number, and so on. So it's a random digits sequence table, basically. Okay. In the table design, the first column is a line identifier. So basically this line is only for you to easy to refer where you're reading at, because there are a bunch of numbers, very easy to read off lines. And this line identifier will help you to identify where you're reading at. Also, they created some space between the group of numbers. They put 5 numbers in a group, but there shouldn't be any space. The space is not meaningful at all. It's just to separate numbers, so it's easy for you to refer to as well, right? So imagine just endless of digits in a random sequence, one after the other, and that's what the table is for. And also the line identifiers, basically, after you read from 101 line, you continue to read to 102 and so on. Just keep on reading. Okay? Then how are we going to use this table to do a sample? So here is the deal. First, when you have a population of interest, you need to label all the individuals first. So every individual need to have a label. Okay, and the most common way to label is you need to make sure every label has the same number of digits. So for example, if you have 50 individuals, right, and you want to label from zero, you want to label it from 1 to 50. So instead of using 1, 2, 3, you need to have 0, 1, 0, 2, 0, 3 because 50 has 2 digits, right? So for the first, 0 to for the 1 to 9, they only have 1 digits. So you need to have a leading 0 there. And likewise, if you have 300 individuals in the population, then the label will be from 001, 002 up to 300, and so on. Right? So label it first. The labeling process doesn't need to be random. So the random selection doesn't happen here. As long as every individual has a unique label, that's all you need. And then you design algorithm from the random digit table. Basically, you just need to make sure when you read from the table, make sure every individual has the same chance to be chosen. So that's it. And then select position to start on the random digit table. So select a point. Theoretically, if you think about all the numbers a random sequence, then it really doesn't matter where you start, right? If you start from this point or you start from this point, you have no idea what's going to happen afterwards. It's going to be a random selection anywhere you start at, right? So it doesn't matter where you start. But since we're in a class setting, just for the sake of making my grading easier, we want to have the same solution, right? So anytime when we do a random digit table lookup, I will ask you to specifically read from a specific starting point. Just basically so that everyone will have the same correct answer, right? And then lastly, follow the algorithm design. So basically that's the algorithm design. That's pretty simple. Basically, if you have 2 digits in the labeling, when you read from the table, read 2 digits at a time. If you have 3 digits in the table, in the labeling, you need to read 3 digits at a time. It's pretty straightforward. So we follow the algorithm on the random digit table and then ignore any values that's not being used. So basically when you label the population, if you read a number from the table that's not in the population label, you can't choose it. Sample has to be part of the population, right? If you can't, choose something that's not in the population, right? And then you cannot have duplications. So basically, one individual can only be selected once. You cannot choose one individual, more than once, right? So that's the idea. We're gonna go through an example, and this is pretty easy. So once we go through the sample, I think everyone will understand. So College of Business, they want to see how their college responded for the conservation effort. They plan to check if the room light or computer was turned off during the weekend for all the offices. There are 86 offices altogether, and they want to randomly select 9 offices out of the 86 offices to check during the weekend. Use random digits table to select 9 offices for the sample. Right? So first step, label, right? Label the population. You have 86 offices in the population. Should label it. And since it's 86, then the reasonable labeling is from 01 to 86, right? So make sure you have 01, not just 1, right? And then we're going to look up from random digit table, starting from line 105. So, if you have random digit table here, and we're going to look at line 105. Right? So then think about if we start a read, then so the first number you read will be because we have 2 digits label, right? We're going to read 2 digits at a time. So the first number read will be 95. I'm going to make this a little bit bigger so it's easier to see here, right? So it's 95. And once a digit is used, you can't reuse it. You can't use it again. So the 95, the first 2 numbers are used. We need to go continue to the next number to read, right? So next number will be 59. And then continue. The next number is 2, right? Even though there's a big space, the space doesn't mean anything, right? So 2 and 9 are the next 2 numbers we read, 29. And then 40. And then 07. And then 69. And then 97. And then 19. And then 14. And then 81, right? And then 60. And then 77 and 95 and 37 and 91 and so on. You just keep reading. So then when do we stop? So then you need to check on the how many individuals do you want, right? You want to have 9 offices, so we need to choose 9 offices. The label is from 01 to 86, don't forget. So that means 95, it cannot be our sample. It's not in the population label. We don't have an individual in the population as 95, right? But 59 will be good, right? That's part of it. And 29 is good. And 40 is good. And 07 is good. And 69 is good. It's in the range. And 19 is good. And 14 is good. And 81 is good. And you count how many other, 1, 2, 3, 4, 5, 6, 7, 8. We just need one more, right? So 60 is good. Then again, and then before you call it done, check the digits you choose. Are there any duplications? If there's no duplications, you're good to go. If there is duplication, make sure you only keep one of them. So you need to keep reading on one more. If you have one duplication, you need to delete one of the duplications. Okay, so then whatever offices with these labels will be a good random sample. Okay, so using the random digits table is pretty straightforward. Right, so here we have the first animal for attendance check. This is a kangaroo. There's a little baby here. So next chapter, we're going to talk about producing data experiments versus observational study. So for any research, it will be either observational study or experiment. The differences is in observational study, the researcher doesn't control the individuals in the study to do anything special or different. They just observe them, right? It could be observing directly, but it could be also indirectly. So the idea is they don't put any influence on the individual in the study. On the other hand, experiment will deliberately impose some treatment on the individuals. So they're going to ask the individuals to do something different from the regular day life, right? So that would be experiment. And only experiment can imply causation. This is very important. The big reason that we want to differentiate between observational study and experiment is because of this. So if you want to design a study to imply something is caused by something else, and you want to conduct just one study to prove your point, you better use experiment, because observational study doesn't imply causation. And why is that? Just think about, a lot of the study about human subjects are observational study. For example, there are many studies showing smoking could cause lung cancer, right? So most of these studies are observational study. So what they do is they're going to send questions to uh, the the people who, you know, and ask them their smoking habits and ask their health conditions, lung cancer, do you have a lung cancer or not? Or maybe they just study the patients who has lung cancer and um, to see how many of them smoke, how many of them don't smoke, and then by comparing that, they can get some conclusion out. But when you think about the design of the study, the researcher doesn't control anything. They're just observing if there is a relationship between smoking and lung cancer, and they try to put a cause in there. Um, but you know, for causing lung cancer, there could be a lot of other factors could contribute in that. So, for example, does that person has a family history of cancers, right? Or the person who has lung cancer, even though he smoke, but maybe he has he work in a mining place, so you know the air or you know the living environments may be different, right? So there are many unknown factors that could contribute to the outcome of the study, but in observational study, none of them are being controlled. So, but if you design a good experiment, then you know um, it can give you causation from just one study. So, for example, if you want to design a study for smoking and lung cancer, what you can do is you're going to screen some people who are about a similar age and a similar health condition, and there are similar working environments, and they're all clean of family history for cancers. And then after that, you're going to randomly divide the group, you know, into maybe 2 or 3 groups, and then for one group, you tell you know they cannot smoke for you know maybe 3 years, and then the other group they smoke maybe 2 cigarettes a day, and then for the other group, maybe they can smoke 10 cigarettes a day, and then you know you follow them 3 years, and then you check how many cause lung cancer, how many has no cancer, and then you know in this case, everything is controlled to be the same. The only difference is you know the smoking, right? They're told to smoke in different ways. So this way, if something happens, if there is a difference between the groups, the only factor that could cause the difference will be the smoking. So that's the causation right there because everything else is being controlled, right? So observational study and experiment. And in either of the study, when you conduct a study, there will be different variables being collected, and some variable is called a response variable, and there's explanatory variable. So you need to understand the different term here. Response variable is just like a dependent variable if you learn from other course as a dependent variable. That's measuring outcome of the study. And the explanatory variable is like an independent variable. So that's a variable for something that causes the response. Okay. So let's look at some practices. If a study of a cell phone and the risk of brain cancer, and look at a group of 469 people who have brain cancers, and the investigators matched each cancer patient with a person of same sex, age, and race who did not have brain cancer, and asked them about the use of cell phones. So then, is this observational study or experiment? Obviously, this is an observational study, right? Because the researcher didn't impose any, you know, condition to the individuals. The people in the study are not doing anything different from their regular day life. They're basically just being observed. So it's observational study. The researcher has no control over them, right? What are the explanatory variable and the response variable? So when you read through the questions, you can see there are different information being collected. So one thing is use of cell phones, right? So that's a variable, yes or no, right? And then the other thing they measure is whether they have brain cancer or not, right? Yes or no, right? So in that case, which one is explanatory variable? Which one is response variable? If you struggle with this, I can give you a good strategy. So put a cause word between the two variables. So do you say having brain cancer cause using cell phone differently, or using a cell phone will cause brain cancer to be different? Which one causes which? And of course, use of cell phone will cause brain cancer, right? So that's the that's the case, right? So use of cell phone causes brain cancer. In that case, brain cancer is response variable. The one being caused, that's the outcome. And use the cell phone, that's the explanatory variable. That's the contributor to the response, right? Okay. So if you get confused, try to put a cause word in between the two variables. That's a very effective way to do it. And then next question, if the study shows 80% of those people with brain cancer use cell phone versus 50% of people who didn't have brain cancer use cell phones, okay, conclude the cell phone use causes brain cancer. You know, observational study doesn't really give you a good causation. So we can't conclude a cause here because this is not an experiment. Well, someone may ask, because we just mentioned smoking causes lung cancer. All the study about that is observational study. And why do people believe that? Why do we now, broadly, take it for granted that smoking will cause lung cancer even though it didn't do an experiment, even though everything is observational study? Why do I believe the cause in there? That's a very good question. So here's the deal. If you just have one study, observational study, showing the smoking causes lung cancer, then people would not necessarily will believe it. But what if you have 100 independent study showing the same thing? Even though they're all observational study, but they are getting exactly the same conclusion. So that's when you will, believe in the results from the observational study, right? You have independent study and confirm each other, so that that will be they can prove the case. But for experiment, you don't have to have that many confirmed independent studies. It's just one experiment. If it is very, very well designed, people will believe it because experiment is a lot more powerful than observational study. It can give you the cause by controlling all the other factors. It has to be a well-designed experiment, not just any experiment, right? So there are some silly experiment designed in a way and making no sense. They're not going to believe that. So for example, there is newspaper talking about a silly study. So the researcher, just some teachers in a camp, the researcher, they declared wearing a parachute is not gonna protect you any different from wearing a backpack when you jump off a plane. How do you believe? How do you think of that? Do you believe their results? Do you believe their, statement? But they are able to design the experiment to prove that. So here's their design of the experiment. They have a small airplane landing on the grass, and then they have a bunch of school kids, maybe 7 or 8 years old. So they randomly randomly divided the students into two groups, and one group will wear a parachute, and the other group will wear backpacks. So then each of them would jump off the airplane, a small airplane, so maybe about 4 or 5 feet high above the grass. So then they find out, wearing parachute doesn't really protect the people, the students, better than the backpack because nobody get hurt, right? So that is an experiment, but it's not a well-designed experiment, right? Okay. So then we have a few different examples just for you to um, able to identify observational study and experiment, and also able to find explanatory variable and a response variable and stuff like that. So for example, here's another one. Many studies have found people who drink alcohol in moderation have lower risk of heart attacks than either non-drinkers or heavy drinkers. And now the research is interest. Does alcohol consumption also improve survival after a heart attack? So if someone has a heart attack, and what will be the best way to help them survive? Not drink at all, drink a little bit, or drink heavy, right? So a study followed 1,913 people who were hospitalized after severe heart attacks. And for those people studied, 47% of the people didn't drink, 36% drink moderately, and 17% drink heavily. And then they're followed for 4 years. And then they basically just check if they have survived or not. Okay. So then is this observational study or experiment? Did the researcher apply any condition to the people in the study? Are they being told to do anything different? No, then this is observational study, right? They're just being observed. They're not being told to do anything different. Then what's the explanatory variable? What's the response variable? So you need to identify the variables being recorded. So one variable is if they die or not, right? If they survived or not. And the other will be drinking habits, right? How much they drink. It doesn't specifically list the variable, but you can make up the variable name, right? So drinking habits versus died or survived. Which one is response variable? Which one is explanatory variable? Right? So if you get confused, try to put a cause word in there. Does survive cause drinking habit to change, or the drink habit to cause survival to change, right? Which one makes sense? Then we should realize response variable is survival, explanatory variable is drinking habits, right? Okay. And then what should you conclude when you see that fewer of the moderate drinkers died after 4 years as a result? We do see moderate drinkers has fewer people dies as a result, but we cannot conclude moderate drinker will cause people to survive better. There's no causation here in observational study. What we can do is we put some soft word. We say drink moderately could or have a chance of, or may help people survive after heart attack. So after you put a soft word, people say just maybe. We're not sure, but maybe, right? So here are three terms that exist in experiments. So most people want to do experiments because they're more powerful. But sometimes experiments is hard to do because there are some laws against it. So you can't really use human subjects for experiment if the experimental condition will harm people, right? Like smoking. Smoking will harm people, so you can't force people to smoke if they don't want to. So it has to be observational study, right? So there are three terms: subjects, factors, and treatments. So please, just get familiar with the terms. It's pretty easy if you spend some time with it. Subjects, the individual studied in the experiment. So whatever objects being studied in the experiment, we call that subjects. And the factors, factor is just another name for explanatory variable. If you know what the explanatory variable is, that's the same thing as a factor if that's an experiment study. And treatment, any specific experimental condition applied to the subject. All right. So you could have one factor, but you could have many, many treatments for that factor. Okay, so for example, let's look at a question here. A post-lunch dip is a drop in mental alertness after a midday meal. So the research question is, does an extract of the leaf of ginkgo tree will reduce the post-lunch dip? To answer the question, a researcher designed the following experiment. 20 people with about the same age and physical condition were selected. Then they randomly select 10 of them to take ginkgo tree extract pill, and the remaining 10 were asked to take a placebo pill. Placebo is a fake pill. It doesn't have any medical effect. So after lunch, they were all asked to read a paper and mark out every letter E in the paper. The number of misses were recorded for everyone. Okay, so basically the idea is if they're more alert, they should have fewer number of misses, right? Okay. So identify subjects, factor, treatment, response variable, and explanatory variable in this experiment. So what subjects? Subjects will be individuals in the study, right? So the 20 people in the study will be the subjects, right? And what's factor? So before you do factor, let's look at what's response variable and explanatory variable. So what are the variables recorded? So we have number of misses as one variable, right? And then what's the other variable? It didn't specifically list, but basically it's the pill type or pill taken, right? So what pill did they take? Okay, so which one is response variable? Which one is explanatory variable? Does pill taken cause number of misses to change, or number of misses will cause pill taken to change? Which one causes which? And the one being caused is a response variable. The one that's causing is explanatory variable, right? So number of misses will be response variable. And the explanatory variable will be, of course, the pill taken. Right? So then if you realize pill taken is explanatory variable, then factor is automatic to be the explanatory variable. Okay? And then what are treatments? Some people get confused between treatment and factor. They are kind of confusing, but spend some time to think about it. Treatment are specific experimental conditions being applied to the individual. So for the 20 people, what different research condition being applied to them? They are being asked for different pills, right? So one is ginkgo pill, and the other is placebo pill, right? So we have two different treatments, but we have only one factor, right? So factor and treatment, they're different things, even though they're related. So think about it. Please let me know if there are any questions. We're gonna have something like this in the test. Okay. And next question, if the number of misses for the group of taking ginkgo tree leaf extract is significantly fewer than the group taking placebo pills, what can you conclude? You know, this is a well-designed experiment, right? So we can conclude ginkgo tree does, you know, help to reduce the post-lunch dip. Right, so this is a second animal for the attendance check. This is a panda. And then another practice, very similar, you know, you can spend some time over this, but it's very similar to the ginkgo tree pill. So summary, in this chapter, we talk about the sample and the population. We kind of briefly talked about different ways of sampling. We have convenient sample, voluntary response sample, and simple random sample, right? Bias in sampling is very, very important. We try to reduce the bias. That's why we do the random sample. But doing random sample doesn't mean you're always gonna get a good sample. There's still a chance you're gonna get a biased sample even though when you do random sampling. It's just that chance is gonna be a lot lower than if you're not, right? So we try to reduce the bias. And then how do I use random digit table? You know, we talk about the table. That's a very easy to use table. And, you know, let me know if you have questions about that. And observational study and experiments for any research. After you read their, you know, study, you should be able to identify that if there's observational study and experimental study, right? And only experiment study can imply causation. So if you want to conduct a study, just one study to prove your point, conduct the experiment. Observational study is not as convincing. And the explanatory variable versus response variable, you know, you should be able to identify that. And then subjects, factors, and treatments and experiments, you should be able to, you know, identify those as well. All right, so then this concludes chapter 8 and 9. Thank you. And we're gonna stop here.